Welcome back to Chapter 9 of AP Statistics. This is 9.2, so we're going to be talking about population proportions. In the next section, we'll talk about population means. All right, let's get started. So, as with confidence intervals, significance tests require a few conditions before you start. It's going to be the same three conditions, but there's a little caveat. It's not going to be exactly the same. It's going to be the same names, not exactly the same conditions you have to check. So random condition, same thing. It has to be a random sample that the data comes from. 10%, same thing. The sample size has to be less than 1/10 of the population. So if n is the sample size and big N is the population, you basically write it like this. N is less than or equal to 1/10 of big N, the population. Here's where things get a bit tricky. The large counts are normal condition. Now, in confidence intervals, you used n p hat and n times 1 minus p hat. Here, you're going to use n p naught and n1 minus p naught. You might be thinking, what is the difference? It's just a different look for p. It's actually quite different. So p hat is the sample proportion. If you took a sample and you got 72% of students were passing the class instead of 60, I'm using the same metaphor from the previous video. So if you didn't watch it, basically the situation is 3 years ago, the school conducted a survey and they found out that only 60% of the school was passing the class. They used new textbooks and now they're testing it again to see if they improved. The null hypothesis would be that it didn't improve, it's still 60%. The proportion of students who pass the class is 60%. The alternative hypothesis is that it is greater than 60%. So if you did a sample and you got 72% as your new proportion, if you were to create a confidence interval for that, you would use 72.72 for p hat. Here, you would use 0.6, even though you took a sample and you got 0.72. That is the sample proportion. You still use the null hypothesis proportion. P naught is the null hypothesis. It's whatever you say the parameter is equal to in the null hypothesis. Now, that's the difference. You still have the 0.72 value in a significance test, but you have to use the null hypothesis when checking the large counts condition. Because what we're doing is we're assuming that the null hypothesis is true. That is what everything starts with. Before, when I was explaining the p-value and how to interpret it, I said assuming that the null hypothesis is true. That's what we do in significance tests. We assume it's true, we err on the side if it's true, and if not, then if we have convincing evidence for the alternative hypothesis, that's when we reject the null hypothesis. So this is what you use. Don't get confused by this. This is for confidence intervals. All right, now that that's out of the way, test statistic. We had similar stuff in confidence intervals, but this is a bit different. You notice that it's Z. Z, it's important because when we get to means, it's going to be something else, and as you might guess, it's going to be T. Okay, we're not there yet, though, so Z. The test statistic Z is going to be equal to, the general formula for test statistic is statistic minus parameter over standard deviation of statistic. For proportion specifically, it's going to be p hat, the sample statistic, minus p naught, the parameter, the null hypothesis proportion, over the standard deviation of the sample. And how do we find the standard deviation of a proportion sample? Square root of p naught times 1 minus p naught over n. Why do we use p naught? Because again, we are assuming that the null hypothesis is true. So no matter what, we're going to use p naught wherever we have a choice. Here we don't have a choice because it has to be something else other than p naught. So we have to use this statistic. We assume that this value is correct because we're assuming the null hypothesis is true. So wherever we get the chance, we use p naught. Okay, now that that's out of the way, that's the formula for Z. You might need it if you're going to show work, which you definitely should. You definitely should show work when you're doing calculations. There's also a calculator way to do this, and I'll talk about that in a second. But first of all, here's the test statistic. What do you do after you get the test statistic? So once you get the test statistic, what you're going to be doing is calculating the p-value. This is a Z-score, right? So if you If you use normal CDF with the z-score, you're going to get an area, and that area is going to be the p-value. I won't do an example with this. The example I will do would be using the calculator, but if you're if you don't want to use the calculator or you don't know how to, for example, then what you basically do is you find the z value, the test statistic, you plug that into normal CDF with that as your lower or upper bound, depending on whether the alternative hypothesis is less than or equal to. Then you do normal CDF of that, and then a really big number either way. And then you use 0 and 1 because it's going to be standardized curve, and you're going to get some area, and that's going to be your p-value for the significance test, and that's where you're going to base your answer off. So with that out of the way, let's talk about the one sample z-test for proportion. This is on your calculator. So if you go to stat, we've done stuff with distributions, we've done with confidence intervals. Now we go to stat tests. It might be called something else, maybe tests or anything, but you go to one prop z test. The one is for, you only have one. Prop is proportion. There's also two prop z tests. That's going to be a future chapter because we don't have two populations. We only have one. And z, because we're using the test statistic as z, and test. It's a significance test. So one prop z test. You do that, you're going to get p naught. You need p naught. So let's try our example. We have p naught equals 0.6. That's what we assume to be true. The number of successes. Okay, let's say we survey 50 students. That's what I mentioned in the previous video. We asked 50 students, and we find out that 36 of them are currently passing. That's a 0.72. That's why I chose those numbers, if it's with our previous example. So our successes would be 36, and n, the sample size, would be 50. Now, what's our alternative hypothesis? Like I said in the previous video, our alternative hypothesis is going to be it's actually greater than 0.6. We're assuming that we're suspicious that the new textbooks would improve the student pass rate. And it did. It is 0.72, but is that convincing evidence that it improved it? That's what we're trying to find. It is evidence. It's not. We don't know if it's convincing evidence or not. So we plug in for the alternative hypothesis. We say prop is greater than p0, p naught. We plug it in. What do we get? You have to click draw on the calculator, and it'll give you a curve. And once it gives you the curve, there's a small p-value down there, and that p-value is what you want. It's gonna be 0.0416. Now, before we even did this, we should have identified a significance level alpha. We're gonna assume it's 0.05 since we didn't establish anything else. It's gonna be 0.05 as long as the problem doesn't state otherwise. So we get 0.0416 as our p-value. Is that it? Well, no, we have to actually write a response about it, but I'll show you how to write a response soon. First of all, does this support, what does this mean basically? Well, it's less than 0.05, right? Which means we reject the null hypothesis. It's small enough that we can reject the null hypothesis and say that there is convincing evidence for the alternative hypothesis, meaning the new textbooks worked. We have convincing evidence that it did. Of course, we might run into a type 1 error. We have no way of knowing that, by the way. We might run into a type 1 error, and we reject the null hypothesis when it's actually true. But the probability of that happening is 0.05, which isn't nothing. It's still a value, but we are pretty confident that our answer is true because we have no other way of doing it. We could have a significance level of 0.01 to decrease the probability of getting a type 1 error because, like we said in the previous video, 0.01 or the significance level is going to be the probability of getting a type 1 error. But for this example, we basically did it. That example I was stretching for the past few two videos, we solved it. There is convincing evidence that the new textbooks worked and the pass rate improved. Voila. Okay, time for how to actually structure your response. We start by saying we want to test at the alpha equals blank level. Blank you fill in. It's usually going to be 0.05. The problem might ask for something else though. And then you write your two hypotheses, the null and the alternative, and make sure to define what your parameter is. You say where P is the blank based on what the problem tells you. After that, you test the conditions. You say if conditions are met, we will construct a one sample z-test for proportions. That's what you write at the alpha equals blank level. You might repeat it, but it's better to say it twice than never say it at all. So that's that. Then you write the three conditions: the random, the 10%, and the large counts or normal condition. And you show that all of those conditions are true. And it's going to be true. If they give you an FRQ about this, it's going to be true. On an MC, it says, if it says, can you use it? Then it might not be true. Like, can you do a one sample z-test for proportions on this sample? Maybe. You have to check the conditions. It might be false, it might be true. But on an FRQ, if you actually have to do the problem, it's never going to be false. Like, it's going to be there, because otherwise, what problem are you going to do? Then you actually do the calculations. You can use the calculator to get it, but you should also show work. You should write the z value you got, you should write the p value you got, and then you write your concluding statement. You say, because blah, 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 there is convincing evidence, or there isn't convincing evidence. We reject the null hypothesis, or we fail to reject the null hypothesis, and so on. All right, let's do an example, shall we? Okay, so this is about, with this we actually did in class. It basically says that, is there an advantage to going last? Maybe everything else before you was so bad that the judges are like, oh my God, this is so much better. We choose you. Is that true? Would that happen? So they take a random sample of 600 college students, show them 12 different singers in random order. So that's pretty important, in random order, so that not one singer is always going to be last. It varies. So it says we would expect approximately 1/12 of the students to prefer the last singer they view. Because order doesn't matter, that means the probability that they choose that is just 1/12, assuming people are robots and they just randomly choose one singer to the width. In this study, 59 of the 600 preferred this last singer they viewed. Do these data provide convincing evidence at the 5% significance level? So 0.05 is going to be the significance level that there is an advantage going left. Okay, we might have to refer back to this for some time, but let's start with our response. We want to test at alpha equals 0.05 level. We said that in the problem. What's our H not going to be? Well, we know that assuming that there is no advantage, the proportion is going to be 1/12. We can write as a fraction or as a decimal. Fraction is going to be more accurate since it's not going to be a nice terminating decimal. This is our null hypothesis, because that's what we expect if nothing is true, like if everything's the same. The alternative hypothesis, we say H is going to be what, less than or greater than? It's actually going to be greater than, because we are saying, well, what if there is an advantage to going last? We're not saying what if there's a disadvantage to going last. This is asking, is there an advantage? So we have to say P is greater, because the proportion of people who pick the last singer, it should be greater if there is an advantage to going last. And of course, we have to state what our parameter means. So where P is the proportion of students that prefer the last singer that they saw. Okay. Now we check our conditions. So if conditions are met, we will conduct a one sample z-test for proportions at the alpha equals 0.05 level. All right, now let's check our conditions. Random, yes. In fact, it was a random sample of 600 students. And not only that, also it was a random order. %, well, 600 is going to be less than or equal to, or sorry, yeah, less than or equal to 1/10 of the entire population. We can assume that there are at least 6,000 people at the school. So there should be at least 6,000 people at a college. So that solves our 10% condition. And large counts are normal. Remember, we use P naught here. So 600, P naught is 1/12. That's going to be equal to 50, which is greater than or equal to 10. And then we have NP naught, N1 minus P naught, sorry. 600 times 1 minus 1/12, we know that's going to be equal to 550, which is also greater than or equal to 10. So all three of our conditions actually work. Surprising, I know. And now we're ready to actually do the calculations. I'm going to clear the rest of this to save some space. But now it's time for calculations. What do we got? So first of all, let's plug it into our calculator. Let's do that first and then test. So we go to stat tests. We go to one prop z test. Our p naught is going to be what? 1/12. Successes. So it actually said 59 out of the 600 students said that they prefer the last singer back in the prompt. So successes would be 59 and the sample size would be 600. What's our alternative hypothesis? We said p is greater than 1/12. So prop is greater than p naught. Plug it in, what do we get? We get a p-value of 0.0919. Okay. Immediately, what do we see? It's greater than 0.05. So it's not small enough, and therefore we fail to reject the null hypothesis. We can't do that yet. We have to actually show our calculations. So I'm going to get rid of this, pretend you never saw it. Now you write it as you would do it if you were doing it by hand using normal CDF and everything. So z is equal to p hat minus p naught over square root of p naught times 1 minus p naught over n. All right, let's calculate this. P hat is 59 over 600 minus 1/12. So you might want to do that first, get an answer for that, and then, plug that in so that it's a smaller step, or you can do it all at once if your calculator supports that. So it's going to be over square root of p naught's 1/12, 1 minus p naught's 11/12, over the sample size of 600. You basically plug that into your calculator. Make sure you use p naught. That's another important thing to do. You cannot use p hat, even though that's the sample. You have to use p naught. So you plug it in, what do you get? You get a z value of 1.329. And there's also another thing you have to do when you're doing this. I don't have space down here because we also have to calculate the p-value here. But you have to draw the distribution, and you write, well, if this is the mean, or this is, the mean of the distribution, which is the parameter, 1.39. So let's assume this is 1 standard deviation, 2, and 3. It's going to be somewhere around here. And then you shade in the other area. You say this is 1.329, your z-value, and then you draw an arrow here and you write area equals, and then you write your p-value. We don't know that yet in air quotes because we actually do, but if we were to hand do the problem, we wouldn't know that yet, so just leave it blank there. Then now comes the fun part. We use normal CDF. It's been a while since we've done that. You go to you go to distributions and go to normal CDF. Your lower bound, so we're going to actually be looking for greater than, right? So your lower bound is going to be 1.329. Your upper bound is going to be a really big number. You can do infinity if your calculator supports it, or like 1 million. And mean is 0, standard deviation is 1 because it's standardized. And you get, you basically type this into your calculator. I'm going to write it down saying using technology. And surprise, surprise, you get 0.0919. Who would have thought? So that's going to be your p-value. You box it or whatever, and you're ready for the next step. You can also write area equals 0.0919. Final step is concluding statement. Because 0.0919 is greater than alpha, which is equal to 0.05, we fail to reject. I'm just going to write H now. You should write the null hypothesis. And there is convincing evidence. Sorry, there is not convincing evidence that basically of the alternative hypothesis. And you should write like in context, we fail to reject the H naught, which states that or whatever. But I'm just writing this briefly. That's going to be your concluding statement, unless the question asks you for something else like, What happens if you make a type 2 error? What are the consequences of that? And so on. Or what type of error would you make? What are the consequences of it? Because this would be a type 2 because we failed to reject the null hypothesis. What if the null hypothesis was indeed false? Then we would be making a type 2 error. And then you can explain the consequences of that, which actually would be, we can actually do that here because we have enough knowledge to do that. If we were to make a type 2 error, meaning we fail to reject the null hypothesis, which means that we say that students do not prefer the last singer they saw. There's no advantage to going last. When in reality, there is an advantage to going last. Then the consequences would be that no one would suspect a thing, and most of the people who win would usually be going last. That's basically what would happen. On a there is going to be a bias when no one knows there's bias. That's basically the consequences. All right. We got this far on our previous slide about stuff. We have some things to add there. Two-sided tests. So we've been talking about what happens if it's greater than, what happens if it's less than, what happens if it's not equal to. P is not equal to 0.6. Let's say that. We just don't know what the new textbooks did. We want to find out what they did. Right. Here, it's going to look like this. It's area on both sides. So you do something very similar. You would calculate the z value for whatever you got. Let's say you did get 0.72 in this sample as well. That would be up here, not down here, because 0.72 is greater than 0.6. So I don't know why I drew an arrow over there. Okay. It's going to be on this side. Now, you find the z value. You get the p value, actually. You do the same thing. You get the area. Now, if you were to do this by hand, you would get the p value. That's not it, though. You would also have to multiply by 2 to account for the area down here. This extreme or more extreme, it goes both ways this time. And that you have to compare to the significance level. That's basically what you would do if there's a two-sided test. As for confidence intervals, which is another thing you can do, I'm not really going to go over it because the entire of chapter A was about confidence interval. But basically what you can do is, well, we took a significance test. It says that we reject the null hypothesis. Let's say we reject the null hypothesis. Well, if P naught isn't true, then what is going to be the actual parameter? That you would use a confidence interval. You would use your sample proportion that you got, construct a confidence interval at a 1 minus alpha confidence level. Alpha is going to be 0.05, then your confidence interval is going to be 0.95 or 95%. So it has an inverse relationship like that. Now, you would construct the confidence interval and you would say, we are, let's say, 95% confident that the actual parameter falls within this interval. Or you would basically do the same exact thing. That's if you want to know the actual parameter. Sometimes you won't be asked that. You could actually be asked a double whammy. You know, first conduct a significance test. If you reject it, then construct a confidence interval to estimate it, and so on. There's actually a relationship between alpha and the confidence level. Basically, a significance test of significance level alpha gives us similar information to a confidence interval, confidence level 1 minus alpha. One last thing is power. Power is going to be basically the probability of making a type 2 error. And it's related to that. So I'll tell you one in a minute, but basically we're saying, let's say we have a mean of 0.6. Basically, that's our null hypothesis, right? If the sample, or if it actually was 0.8, basically we failed to reject 0.6. But what if it is like not 0.6? Basically, what if the alternative hypothesis is true? That's what the power. That's what I meant by a type 2 error earlier. The power says, well, if the actual parameter was 0.8, for example, what is the probability that we would detect it and actually reject the null hypothesis? Sometimes you say the null hypothesis is true, you fail to reject it, when actually it's wrong, and that's the type 2 error. Or you actually detect that the null hypothesis is wrong and you reject it. How do you calculate that? I'm not going to go too in detail about that, but basically, if you have this 0.6, and let's say you had a sample of 0.72, right? What you basically do is if zero point 0.8 is the actual um, parameter, then you draw the same line to 0.72. You calculate this area, and that's going to give you the power of the sample. Now, I use 0.72 arbitrarily, and actually that might confuse you because 0.72 was the sample in the previous one. Actually, this doesn't use a sample. It uses the 0.05 or the alpha. If alpha is not 0.05, then use something else, whatever alpha is. But I'm using 0.72 because that's just a number instead of using alpha, which 0.72 is the z value of alpha in this scenario. I probably should have clarified that, but you basically find out where alpha is, find the z value of that, or find the actual value of that, what number it is. Then you use that same number in a sampling distribution of 0.8, and then now you use normal CDF to find the area, and that area is going to give you the power, which is represented with this symbol beta. And like I said, the probability of a type 2 error is going to be 1 minus beta. So that's going to be it for this video. It's actually a bit longer than 9.1. Pretty expected because 9.1 was just an introduction. But this basically covered population proportions. And next time we're going to be talking about population means. So look out for 9.3. See you later.